Okay, welcome to lecture 8, Fusion Welding Fundamentals for Manufacturing Process. Today we're going to start with Submerged Arc Welding. This is a special type of arc welding where the welding actually occurs beneath the flux. That means the material that actually used to prevent environmental contamination to the welded zone, and also to facilitate the proper welding or to keep the arcs alive. So first of all, in submerged arc welding, instead of a flux covered electrode, granular flux and a bare electrode is used. That means the electrode will be bare. Okay. That means it will not have any coating. Sometimes it can have a copper coating to prevent the electrode from degrading because of the environmental impact. And granular flux are used. That means the flux powders are used to protect the environment. And the arc between the electrode and the job is heat source and remain buried under the flux. That means the whole welding process is conducted below the flux powder. That means the operator cannot see where the welding is being conducted, but there will be guidelines for that. And there is no problem with the light reflection due to the arc. Okay, and the flux serves as a shield and protects the molten weld pool from atmospheric contamination. And both DC, AC, both can be used, but if we use direct current reverse polarity, that gives high penetration. That means to weld a highly thick material, you might want to use direct current reverse polarity system for DC, and DCSP for high deposition and minimum penetration. If you need less amount of penetration but huge amount of electrode deposition into the welded zone, then you have to use the direct current state polarity. And this is the schematic diagram for submerged arc welding. Most of the cases, drive rolls are actually used to continuously feed the electrode in the welding zone. Okay, that means this drive rolls actually rotate this way. Both rotates, one clockwise, another one is anti-clockwise, to draw the welding rod from a pool of welding rod, and then it feeds the welding rod into the space where welding is being done. And there is the power supply, and the arc that is generated is buried under the flux. That means flux powders will be on top. The arcs will be generated below this flux, and the operator cannot see where the welding is being done. Okay, and this is the weld pool where welding has been already completed. And this is a real life image of submerged arc welding, where this hose, this pipe actually provides the required flux powders on top of the welded zone, and this one also used to provide the flux powders into the groove that has been cut for welding. For example, if you want to weld two workpieces like this, then to provide flux in this region, firstly, small amount of flux is introduced in this region, and then large amount of flux is introduced to cover all the space. Okay, and this is the electrode holder. Through this electrode holder, the electrode wire is provided with the help of drive roll, and then welding is being continuous. Okay, any question? All right, the advantages of submerged arc welding includes high productivity process due to high heat concentration. Because of the flux material on top of it, heat concentration is much more, and the weld deposition rate is high due to continuous wire feed. Since the electrode is fed continuously, so the weld deposition rate is also high, and hence the single pass welds can be made in thick plates. Even if you are welding a thick plate, you can obtain a huge thickness. A huge thickness can be considered for welding using submerged arc welding. For example, if you don't know what is single pass weld is, I would like to explain that. For example, you have a welding. You have to weld the material like this, and then this is the cut AS that has been prepared. And then in this case, sometimes a small zone has been welded first, then another welding is done in here, then another welding is done in here, another pass is done. Like this is the multi-pass welding. But if you use the submerged arc welding, then in that case you don't have to do it 3 times to weld a highly thick material, but you can do that in a single pass. Deep weld penetration can be obtained, that means strong bonding can be obtained, less smoke, and the flux heats the arc, hence the improved working condition. Okay, the operator does not have to wear the special glasses to protect their eyes. And submerged arc welding can also be automated. In most of the cases, these types of weldings are automated because the operator cannot see where the welding is being conducted. So automation is a good solution for that, and that is in most of the cases that is what is used for submerged arc welding. And there is no chance of spatter of molten metal because the arc is beneath the flux powder, so spattering is prevented. Okay. And disadvantages include, since the operator cannot see, so there is a possibility that the proper penetration has not been obtained, and also the direction sometimes cannot be maintained. Which way welding is being conducted, that cannot be maintained. And the process is limited to welding in flat position because you cannot weld in the vertical position because the flux powders will not be in place if you weld in vertically or on the roof. Okay, this is only limited to the flat metals more than and in the case of this submerged arc welding, another limitation is that the workpiece thickness has to be more than 4.8 millimeter. Otherwise, there is a possibility of burning out the workpiece. Instead of welding, there will be void created. Okay, so more thicker, more better welding can be obtained from submerged arc welding. And the process requires edge preparation. That means you need to have the edges prepared properly, accurate fit up on the joint, and otherwise the flux may spill through the gap and arc may burn the workpiece edges. That means if the space between two workpieces should be very close together, that means this space should be very close together, otherwise powders will get through that part, small zone. And also at the same time when the welding is being conducted, this zone may burn out, and the liquid metal may drop down from this region. Okay, so to prevent that, you need to prepare the edges properly, so that, and also keep the gap in a certain limit so that you don't ruin the welding. And the flux is subject to contamination that may cause weld porosity. That means if the flux has any contamination, then that flux may cause porosity in the welding job. Okay, that will produce gases, and that gas will be trapped into the welded job. And the application is mainly for the fabrication of pipes, penstocks, large pressure vessels, etc. And automotive aviation industries also use this type of submerged arc welding to join the various highly thick metal plates. And these are some application example. Like if you are joining a plate like this, then you have to keep it always in the horizontal position, otherwise you will not get the proper welding. Okay, and also linear welding can be done like this way. Welding can also be done using submerged arc welding. And the only limit, you need to really take care of one thing, that is the position has to be horizontal, and you have to weld from the top. Okay, That means this workpiece will rotate, but the electrode will stay in the fixed position here. Okay, any question? That's all for submerged arc welding. If you have any question, please ask. All right, so the next one is the thermit welding. This is a chemical activation process that is used for thermit welding. In the case of this chemical welding method, the thermit mixture that compound consists of finely divided aluminum and iron oxide. A mixture of aluminum and iron oxide at a ratio of about 1:3 by weight is used as a thermit mixture. That mixture actually reacts to produce heat. Okay, the mixture is not explosive and can be ignited only at a temperature of about 2800 degrees Fahrenheit. When you raise the temperature of the thermit mixture to 2800 degrees Fahrenheit, then the aluminum and iron oxide actually reacts, and aluminum oxide is produced. Okay, aluminum oxide is produced with leaving pure iron in the zone. And aluminum oxide has a very low density compared to iron, so aluminum oxide actually comes out of the liquid and accumulates on the top of the container. Okay, and the pure iron is used to conduct the welding process. And the chemical reaction requires only about 30 seconds, and when the temperature is raised, and the temperature that is developed is 4500 degrees Fahrenheit, which was initially 2800 degrees Fahrenheit. Okay, and then when the reaction is done, then temperature is raised to 4500 degrees Fahrenheit. The resultant products are a highly purified iron, actually steel, and slag, which floats on top and not used. That means this iron oxide actually floats on the top of the container and is not being used, but the iron that is accumulated on the bottom of the surface is used for conducting the welding process. Okay. So this is the schematic diagram of the welding process, where this is the container where aluminum and iron oxide is mixed together, and then when the container is heated, then the iron will steel from the thermit reaction will accumulate at the bottom of the container, and the slag, that means the aluminum oxide, is accumulated on the top of the container, and the welding zone is prepared like this. This is a rail joining method where the sides are constrained by a sand mold, and then the two workpieces are placed at a certain gap, and then highly purified iron at high temperature is poured into the zone, and when solidified, then it's kind of a casting process. The mold is removed. Once the mold is removed, then you will see like this, and when the temperature is still high, the mold has to be released, and then this extra metal is cut off from the system. Okay, and this is the mold preparation method using the sand and the fire brick, and then to put the highly molten material of only iron in the joint welding zone. Okay, any question?
So what is the function of fire brick?
The fire brick is just to prevent make the mold. Okay, instead of using all the mold, you can reuse these fabrics. Once the welding is done, then you can use it again. Okay, that's the main purpose. Okay, any other question?
Sir,
so yes,
sometimes we used welding in to joint rods in the.
sorry, I could not hear you. Hello.
Sometimes we used welding to joint rod in,
Yes.
like, in pillar.
Okay.
What types of welding is used here?
In most of the cases, that's shielded metal arc welding. Okay. This weldings has various weldings has actually various purposes. For example, this thermit welding, this is mostly used for remote areas where you don't have a proper heat source. Okay. In that case, you need to use this type of welding. Okay, because to join the railway sleepers, you cannot use either gas welding or other welding processes. So this welding process is much more suitable for this specific application. Okay, because you need only a small amount of heat to heat the mixture. You can use like various fossil fuels, like you can even burn the straws to raise that much heat, and then once that much heat is raised, then because of the reaction, extra heat will be generated and the pure iron will be in there. Okay. Right. So the advantage of thermit welding is like the heat necessary for welding is obtained from a chemical reaction. Thus, no costly power supply required, or therefore the broken parts rails can be welded on the site itself. Okay. In the remote areas that can be done. And the process is best suitable and particularly in remote locations. Okay, where sophisticated welding equipment and power supply cannot be arranged. The thermit welding is applicable only to ferrous metals because as you know that to weld some metal, you cannot use a different metal. For example, if you want to weld steel, then you have to use steel as a third metal. But if you want to weld aluminum, then you have to use aluminum as a third metal. So otherwise, proper bonding will not be obtained. So since the reaction actually produces ferrous metal, that means iron is produced. So only ferrous metals can be welded through thermit welding. That is the limitation. And process is uneconomical if used to weld cheap metals or light parts. Okay, so it will not be economical because it involves a lot of labor. Okay. Applications include large forging, casting pipes, mill house, and repair works, large fractured crankshafts, welding broken frames of machines, teeth of large gears, forging. Most of the cases for large structures, this welding is used and mostly economical for those large structures. Okay, so the next one is the electron beam welding. In this case, a coalescence is produced from a highly high speed electron, that means high velocity electrons. When strike on a surface, that velocity, kinetic energy of those electrons actually released and that's as heat, and then using that heat we can do the welding. The metal is joined by melting the edges of the workpiece or by penetrating through the material, and usually no filler is used. It's a very sophisticated type of welding. And the process may be used not only to join the common metals, but also refractory metals. That means refractory metals means the metals that can withstand a very high temperature, because electron beam actually produces very high temperature. And because of that, refractory metal can also be welded. And highly oxidizable metals can also be welded, and various superalloys. Okay? That's actually impossible to weld using other methods. This is a schematic diagram for electron beam welding. AC filament is used to generate electrons, and to control the electrons, there is cathode electrode, anode electrode, and focusing and deflection coils. Those are used to control the electrodes. Once the electron is generated in the cathode, then this cathode with high negative pole of DC is attached here. Because of this negatively charged cathode, and the electron is also negative, the electron actually gets reflected and gets concentrated on this region. And once the electron is generated, it doesn't have that much velocity. And once the electrons is concentrated in this region, then because of the anode is positive, the electron is drawn through this line in this way. Electron is drawn this way, so that electron gets sufficient amount of velocity because of this anode. And when electron passes through this, And this focusing and deflection coils actually deflects the rays. Sometimes let's say it is welding in this region, and if you want to weld in this region, then you might have to modify these voltages so that the beam is focused in this region. Okay. Then this is the focusing and deflection coil that is used to conduct the welding in a large location. Sometimes you don't need to do the focusing or deflection. You just place in here, and you can move the workpieces from left side to right side or right side to left side to conduct the welding. Okay. This is another example. And also this electron beam welding requires vacuum. The whole system has to be under vacuum, otherwise electron will not, sufficient heat will not be generated, and you will not be able to control the electron movement. Okay. Okay. Any question? Okay. So any metal, including zirconium or beryllium, tungsten, can be easily welded. High quality weld, and operation is carried out in vacuum. So there will be no weld contamination or impurities. There is no impurity. And concentrated beam minimizes the distortion. That means since the welding zone is very small, so bending or any kind of distortion of the specimen is not occurring. And the cooling rate is much higher compared to other material. Heat affected zone is less, and shielding gas, flux, filler metals are not required in this case. Disadvantages include high capital cost. Initial equipment is very costly. Extensive joint preparation is required. Otherwise, you need to have really close tolerance in the case of when you keep these two workpieces together. There will be minimum amount of gap has to be maintained, so that since the welding will be done in a very small zone, so you need to prepare the edges very carefully. And the vacuum requirement tends to limit the production rate, because you have to do the vacuuming and then place the workpiece, and once the workpiece is cool, then you release the vacuum and then put another one. It takes a lot of time. That is why production rate is very small. And the size of the vacuum chamber also is important, because larger the vacuum chamber, you need huge amount of energy as well as a longer time to achieve the proper vacuum. Okay. And not suitable for high carbon steel, because high carbon steel is very conductive, and cracks occur due to high cooling rate. Okay. High carbon steel is conductive. One of the reason electron gets does not produce enough heat, and also another reason is that because of the high cooling rate, fracture actually occurs on the surface on the welding job. So the steels with high carbon, that means cast irons, cannot be welded using the electron beam welding. Okay, any question? So these are the examples of welding. Okay. Or repairing cracks. If there is a crack, then you do the welding, and then you get this sort of welding here. Okay. Very small welding can be obtained. Okay, so the next one is plasma arc welding. The term plasma, as you know, mass of extremely hot ionized gas. And to obtain the plasma state, gases like argon is passed through a constricted electric arc. When the argon gas is passed through the arc, then gas gets really exposed in a very high temperature and become ionized. And though that ionized gas, when it gets out of the nozzle, that actually called plasma. Okay, and that plasma is high temperature plasma is used to conduct the welding. Okay, and temperature is almost 1500 degrees Celsius temperature can be obtained, and the temperature can also be controlled. Okay, you can raise the temperature or you can decrease the temperature by controlling the ionization process. That means how much gas you are supplying. That depends. The temperature of the plasma jet actually depends on how much gas you have been supplying to the system. Okay, more the gas, more heat will be generated, but there is always a limit. And this is actually two types. One is transparent arc plasma, another one is plasma jet projector. We'll be discussing both of them with the images. this is the transferred arc plasma type system. In this case, plasma gas is provided surrounding the electrode. This is the electrode in here. Non-consumable tungsten electron is used. That means this electron is not consumed. Electrode is the purpose of this electrode is to generate the arc only. Okay. When the arc is generated and plasma gas is passing through the arc, then gas gets heated up and produces plasma. And that plasma actually hits the workpiece in here to join to do the welding. Okay, and sometimes shielding gas is also used on the outer side of the welding zone to prevent the welded zone from contamination or environmental effect or oxidization. Okay, it's a very simple process. Just you produce the arc and then supply the plasma gas. The amount of plasma gas that is supplied that will determine the how much temperature is generated in there, and shielding gas will provide the shielding so that the welding zone is not affected by the environmental oxygen or water molecules. Okay. And since a very high temperature is generated in this location, so there needs to be a cooling process, and sometimes that water cooling nozzle is used in here. Okay, that means the water continuous circulation of water occurs in this region, so that you get the welding zone, the electrode and the electrode holder gets cooled down. Okay, any question? And the next type is plasma jet projector. So in the case of plasma jet projector, the arc is stuck between tungsten electrode. It's a slightly different type. Here, the arc is generated inside, and the powder, that means the metal powder is actually provided through this region. Okay. Once the arc is generated, then you provide the plasma gas through this, and the plasma gas will go through the arc and will create the plasma. At the same time, the powder that is provided in this location will be mixed with the plasma and it become liquefied, and the liquefied metal along with the plasma gets out through the nozzle and creates the coating. Most of the cases, this type of plasma jet projector are used to create the coating, and you can also do the welding if you want to conduct the welding. Okay, and metal coating can also be done through this plasma arc welding. Okay, any question? And this is the cooling method. Actually, the cooling is done through these holes. And also this is the water cooling system in here that is also used. Okay, for the advantages, plasma arc welding can be used for welding very hard material, that is refractory material, or super alloys can be welded through plasma arc welding. And plasma arc welding process ensures 100% penetration of the base metal. Because of the high temperature, it can produce a very high penetration. It is useful for semi-automatic or automatic processes. Both can be done. Plasma arc welding process produces a very high quality welding, and also plasma arc welding process is very fast and cooling. Because of the high temperature, it is supposed to be very fast. Okay, and if you provide the gas shielding, then it will be a clean weld can be obtained. And disadvantages: need high power electrical equipments. Plasma arc welding gives out ultraviolet or infrared radiations, which is harmful, and sound that is produced is more than 100 decibel, which is also not comfortable. And initial cost of the process equipment is very high. These are the disadvantages of plasma arc welding. Application: there can be many types of application, like spraying of various refractory materials, joining rocket and atomic energy field, stainless steel, titanium, high carbon alloys can be welded. since electron beam welding cannot weld the high carbon material, but plasma arc welding can be used to do that. And the process can also be used for the manufacture of shim welded stainless steel tubes can also be produced at a very high production rate. Okay, that's all about the welding. And since we had our syllabus contains not only welding but also the allied processes. So the soldering, brazing, and brace welding are the allied processes that we need to talk about. I think you already know the soldering method for the printed circuit board. The soldering method is mostly used, and there is brazing and brace welding. We'll talk about that. And in the case of soldering, the melting point of the filler metal is less than 427 degrees Celsius. But in the case of brazing or brace welding, the melting point of the filler metal is above 427 degrees Celsius. The difference between soldering and brazing is in their operation and the temperature, melting point temperature of the filler metal. Okay. So for soldering, it is less than 427 degrees Celsius, and for brazing, it is more than 427 degrees Celsius temperature. So for the first, I'd like to talk about brazing. It is a name given to a group of welding operation in which non-ferrous filler metal melts at a temperature more than 427 degrees Celsius. But the metal that you are joining, the temperature of the metal will be melting point temperature of the metal that you are going to join using the brazing method will be higher than the melting point temperature of the filler metal. That means when you do the brazing, the base metal will not melt. Okay, the only third metal will melt and act as a glue to join the base metals. Okay. And the molten filler metal flows by capillary between heated but unmelted adjacent or overlapping joint members. Okay. To illustrate that, let's say you want to join two pipes. Okay, this is one of the pipe and this is another of the pipe. This white region is basically these are the base metals. The pipes are the base metals, and this white region is the filler metal. Okay, this white region is the filler metal, and the filler metal is placed in this region, and then when heated up, then filler metal melts and penetrate through the joint, so that because of the capillary action, since the joint is very has a very close tolerance, the filler metal actually flows through the joint using the capillary action. Okay, and acts as a glue. Okay, and then the joining is formed. Okay, and one of the application is the radiator. If you want to join the radiators, you place the filler metals like this. Okay, surrounding the joint, and when you heat up using this induction heater, then the filler metal actually melts and flows through the joint. Okay, and produces a perfectly fluid tight joint. Okay, any question? Did you understand the brazing process? So for brazing, the molten filler material actually has two functions. One is wet the base metal surfaces. That means the base metal that is being joined will be first needs to be wet so that capillary action can take place, and it spreads along the joint by capillary action. When the capillary action is activated, then the molten metal will flow through the small space between the work pieces and produce, upon solidification, they will produce a very airtight joint, but there will be no effect on the base metal. And third function is that the adheres and solidifies to form the brazed joint. And here in the case of brazing, capillary actually plays a very important role for producing good brazement, provided the base metal surface are wet by the molten filler material. Okay. Because of the wetting, the capillary action gets more favorable condition for capillary action, and molten metal will flow through the space. And here also sometimes the flux is also used during the brazing. the flux actually melts at a lower temperature than the brazing filler metal. That means filler metal has higher temperature, melting point temperature than the flux. That flux when melts, that actually when you heat it up, flux actually melts first and wets the surface to be brazed, and then removes the oxide films with it and gives the clean surface. Since the capillary when you obtain a clean surface, then filler metal actually melts and occupies that location. But how do we remove those fluxes? Because flux does not contribute to the joining. Okay? And since the capillary attraction between the base metal and the filler metal is at least several times higher than that between base metal and the flux, the capillary action between the metals you want to join and the base metal is very high compared to the base metal with the flux. And that is why when filler metal is molten, and that actually replaces the flux. Flux comes out of the capillary zone, that means the space between the workpieces, and the molten metal actually flows into the narrow space to produce the joint. Okay. And the narrower the joint, better will be the capillary flow. The joint upon cooling to room temperature will be found filled with solid filler metal, and the flux that has been introduced initially will come out and also solidified, but will be found on the joint periphery. That means flux will come out of the joint and accumulate on the joint surface. And the high fluidity of the molten filler metal is also an important factor to obtain successful brazing joints, because the molten filler metal should not have very high viscosity, but it should have very high fluidity so that it can easily flow through the narrow space between the workpiece that you want to join. And I would also like to outline the difference between brazing and the welding method. Surfaces to be brazed are not raised to fusion point, whereas in welding, the two surfaces to be joined are actually melted. In the case of brazing, base metal does not melt, but in the case of welding, in the case of brazing, base metal does not melt, but in the case of welding, base metal actually melts. And the brazing alloy spreads by capillary action, but in the case of welding, you just introduce the filler metal into the place. Okay, there is no capillary action. And welded joint achieved penetration into the base metal. Since the base metal actually melts, so the penetration will occur, but there is no penetration in the case of brazed joint. That means the base metal is not affected in any way. Some of the example of brazing filler alloys include aluminum, silicon, magnesium, copper, zinc, etc. Okay. These are some filler alloys that is used for brazing. The brazed metals that can be brazed, these are some examples of that. And brazing process. To conduct the brazing, it depends on how you do the heating. Okay, the heating is the main thing. Okay, the number of processes are employed to heat the workpiece. Okay, you can heat the workpiece through fuel combustion, through induction heating, through gas heating, anything you can do that. And the method of heating is a major factor that governs the economics of the brazed joint. That means which heating method you are using, that actually determines how much the welding will cost. Okay. And the method of heating is selected after considering the following factors: type of job, what type of job you're going to weld, and type of jobs to be brazed, number of jobs, how many jobs you want to braze, and availability of the required equipment. Okay. These three factors need to be considered before choosing which heating method you want to use. There are several heating methods like torch brazing, furnace brazing, vacuum brazing. Okay. Method of heating according to the method of heating. And deep brazing, sometimes metal and salt bath brazing can also be done. Infrared brazing, carbon arc brazing. Okay, these are all the heating methods. You can do the brazing under vacuum. Okay. Advantages include the brazing can be used to join a large variety of dissimilar metals. This is the one of the best advantages for brazing, which is that dissimilar metals can be joined. And properly brazed joint are pressure tight, so under pressure it will not break. And pieces of greatly different thickness can be easily joined by brazing. If two different thickness plates you want to join, you can do that using the brazing. Okay, but since the fusion is not necessary, that means you don't need to melt the base metals, so it is very easy. And the brazing has the ability to preserve protective metal coating and cladding. Okay, that means if the metal already have some coating on the base metal, the brazing actually protects that, and that is not affected by the joining action. And the brazing can fabricate large assemblies in stress-free conditions. Since there is no melting of the work pieces, so there will be no internal stress developed, or there will be no distortion. Okay, so initial dimension will be fixed, and there will be no internal stress present on the joint. Brazing can preserve special metallurgical characteristics of the metal. Since there is no involvement of the base metal, so metallurgical characteristics will not be changed, and also maintain precision of product tolerance. Precision can be maintained, and the brazing can easily automate it. You can do the automation, and the process can be done more economically and quickly. But if you do the proper analysis based on these three factors, like type of job, how many jobs you want to produce, and also the heating method. Okay. Disadvantage, always there is some disadvantages. Size limitation of the part to be brazed is a major importance. Okay. Large cast section or large heavy plates cannot be easily brought up to the temperature. You need to heat it up to the brazing temperature. So if it is not, then joint will not be prepared. And the brazing requires tightly matting parts to ensure capillary flow. That means the two parts that you want to join, they needs to be polished before you do the joining, so that capillary action comes into effect. Okay. And the flux residue, if not properly removed, can cause corrosion. If the fluxes that has been generated, you don't remove them properly, then it will cause the corrosion. And also the braze joint do not give satisfactory results when used at elevated temperature. Since the joining metal has a low melting point temperature, so it will not give you satisfactory result when operated at a very high temperature. Okay, because at very high temperature, those brazing joint will be detached because of the melting of the brazed the third metal. Application includes pipe fitting, tip tools, or electrical parts, heat exchangers, radiators, and the leak tight joint for pressurized and vacuum system. Okay, leak tight joint can be generated. Okay, that's all for brazing. Please ask if you have any question.
No, sir.
Right. Next one is the braze welding. Braze welding is very similar to the welding. The only difference is that in the case of braze welding, what you do is that the base metal is molten. Okay, and in the case of braze welding, you just heat it up, heat up this zone, and put the third metal into the location. Okay, and then join is achieved, but the base metals will not be affected by the heat. Okay. And this is the braze welding process. You just heat up the filler metal to fill up the joint. Okay, and then these are the base metal, and dissimilar metals can also be joined using brazing. Actually, in the case of brazing, filler metal basically acts as a glue. Okay, to join the metals. These are very general things. And the difference from brazing is used with closely fitted surface, but braze welding is normally employed for making groove like of slot welds. Okay? And in brazing, filler alloy is fed to one or few points in the assembly and drawn into the rest of the joint by capillary action. Whereas in braze welding, the filler alloy is deposited directly at the point where it is desired. Okay, that means in a word we can say that the brazing is depends on the capillary action, whereas in the case of braze welding, you just deposit the third metal into the place where you want to make the joint. And the profile of brazed joint is smooth, whereas the braze welded joint show repulse characteristics on the moving heat source. That means there will be some surface property degradation because of the heating. And braze welding is a process which is intermediate between true welding and true brazing. Okay, that means in the case of true welding, base metal melts. In the case of brazing, metal is delivered through capillary action. But in the case of braze welding, it is in between these two processes. That means in between brazing and braze welding. So the next one is the soldering. In soldering, the melting point of the filler metal is less than 427 degrees Celsius. And in brazing and braze welding, the melting point is above 427 degrees Celsius. Okay. And the various methods used for brazing is also used for soldering. That means the heating methods. Okay. And most of the cases, soldering is done using a soldering rod. That means soldering rod actually acts as a heat source. Okay. You put the you do the joining using the solder, and solder when you bring the solder close to soldering iron, this metal actually melts and the joints are filled up by the solder, molten solder, and produces a proper joint. Okay, it's very similar to the brazing, but only difference is that the solder rod has a melting point temperature less than 427 degrees Celsius. And various soldering alloys that can be used. Mostly tin and lead solders are used, and some other alloys can also be used for soldering. This is the practical method for doing the soldering. This is the heat source or the solder iron, and this is the filler metal, and the joint is achieved by melting the filler metal. And filler metal actually penetrates through the joint by the capillary action. Okay, that's all for welding. Do you have any question? So we have done a lot of weldings, but we also need to learn if there is any defect that can be produced during welding and how to remedy those defects. There are two types of defects actually, due to faulty technique and due to fundamental difficulty in welding. Okay. So difficulty in welding, you cannot easily overcome these defects, but you can overcome these defects with the experience. Okay, faulty techniques. Due to faulty techniques, first defect that can come into effect is insufficient fusion. That means caused by insufficient heat and too much travel of torch or electron. Okay, that means if there is sufficient heat is not generated and you move the torch or electrode very quickly, then insufficient fusion will occur and the joint will be less stronger actually, and the base metal will not have chance to melt properly. Number two is slag inclusion, caused by contamination of weld metal by atmosphere. When the weld metal is contaminated by atmosphere, then slag will generate and usually occurs in multi-layer welding. First welding is done, and then on the top surface you need to remove the slags. Otherwise, if you do the welding on top of the slag, then you will not get the proper welding joint. That will act as a defect. Okay. So before doing the second pass of welding, first layer of welding is done, and then you clean the surface properly, and then you do the second layer of welding. Otherwise, there will be a defect. Okay. And some other causes also there present, like long arc length. If arc is very long and slow speed, less electrode angle, in that case, this kind of slag inclusion defect can also occur. Inadequate penetration, it occurs when root face has not reached the fusion temperature. That means the bottom surface of the welding joint is not properly molten. In that case, you get inadequate penetration. It may lead to cracking. Sometimes it can do the cracking, and may cause by incorrect S preparation. If the S preparation is not proper, then inadequate penetration can occur. using wrong diameter of welding rods. And it should also be noted that the diameter of the welding rod also affects like how much penetration will occur and how much heat will generate, or how much filling will be done. Okay, that depends on the welding rod diameter, that means electrode diameter. And sometimes over penetration can occur, the melting or burning of base metals. You do the burning instead of welding, you do the burning of the metals, and instead of joining, there will be voids present in the joint if you do the over penetration or overheating. Due to difficulty in welding, welding itself has some difficulty. One of them, the welding defect that can occur because of the difficulty is the porosity caused by entrapment of gas, excessive welding heat. If the heat is excessive and if the gases are trapped into the welding zone, then the porosity will occur. Porosity is basically the if you produce a joint in here and there is some bubbles, gas bubbles present on the joint, then this is called the porosity. Then the porosity will occur. And the spatter, like sprinkle, you already know that. And the cracking may cause due to incorrect technique also, but sometimes it is very difficult to avoid. Metals having different contraction than base metal. Okay. Then the cracking will occur. Okay. And the hot cracking may occur due to sulfur content. If the base metal contains sulfur, then there will be defect like sulfur, metal sulfide will be produced on the welding zone, and like welding zone, like the porosity, these zones will be like metal sulfide, and metal sulfide actually act as a defect. And the cold cracking, several factors for low alloy steels, like volume change due to metallurgical change. When the volume change occurs, like on the heat affected zone, there is different volume change than the welding zone. Because of that, crack might occur on these regions. Okay. And the cooling rate, if the cooling rate is very high, then there will be contraction, very high contraction, and because of that contraction, the stress mismatch will occur between base metal and the workpiece on the welded zone. Then there will be crack. And also hydrogen embrittlement. That means hydrogen produces water, which causes rusting. Okay, when the hydrogen reacts with environmental oxygen and produces water, which causes rusting on the edges or surfaces of the material, you cannot avoid these defects. Okay, so these are the welding defects that is produced because of the difficulty in welding. Okay, that's all for welding and from my side of this course, or my part of this course. And please ask if you have any question. Okay, all right, then if you do not have any question, then we can move to general discussion.